A clever and wise boy, Connor, said to me, Mr. Nkume, you might want to expand your horizons in terms of where you travel, because Connor felt that my travel interests were a bit narrow. And so, when I act on Connor's advice and go further, I might actually go to Iceland. Why would one go to Iceland? Because of what they call the Northern Lights. What is the significance of the Northern Lights? I don't know if you've ever seen them. I'll try and pull up a picture in a few seconds as soon as my internet works. Do you see the Northern Lights? These are examples of some of the incredible features or the incredible sights that are produced in Iceland. I think it's the only reason why one would ever go to Iceland, because other than that, it is very cold and of course they have no sun most of the time, or for short periods of time. Northern Lights, how are they formed? They are formed because of the Earth's magnetic field. Charged particles from the sun enter our magnetic field, and as they travel along the magnetic field, these are formed. Of course, a magnetic field is also really important for another reason, because things like butterflies or birds that have perhaps the brain of the size of a pinhead are able to travel for thousands of kilometers and not get lost by using the Earth's magnetic field. So the magnetic field is an important thing for the Earth, but of course, we are not talking about that much of the magnetic field. We're just going to just keep it simple, physics simple, A-level physics simple. All right, so what is a magnetic field? It's a region of space where a magnetic pole or a current will experience a force. What is a current? Right, a current is a moving charged particle, right? So say, for example, I have north and south here, north and south, and I put a charged particle, magnetic pole. It will experience a force, obviously. But then I put a moving charged particle, like an electron. And of course, because it's moving, it's now a current, and therefore will experience a force and will deviate in a certain direction. All right. So, do we understand that? So, what's a magnetic field? It's a region of space where a magnetic pole or a current will experience a force. What are the properties of magnetic field lines? How to draw them? Well, when we're drawing magnetic field lines, certain rules apply, right? First of all, you must draw the field lines from north to south. I hope that's simple enough, right? North to south. Ooh. You must draw smooth curves that do not cross. So you can't have overlapping field lines, for example. And of course, in addition, the magnitude of the magnetic flux density is indicated by the distance between the lines, which means that when the lines are fairly close to each other, we imply that the field is strong, right? But as the field gets bigger, the lines should get broader. I hope that makes sense, yeah? As the field gets bigger, the lines should get have more distance between them. All right. So let's discuss electromagnetism. When we say electromagnetism, what do we mean? We mean the field lines that are produced around a moving charge. And this is a really important thing to think about. We're talking about anything with a plus or a minus, and it must be moving, right? That's what electromagnetism is about. When anything with a plus or minus charge, current is moving. Case 1, right-hand grip rule. Let's look at this very quickly. Where is the right-hand grip rule? As you can tell, I've been trying to make this video 4 times, and each time my device has been crashing. So I'm hoping, praying, wishing that it will go well. So the right-hand grip rule is this. So the direction of the current, as indicated here, is going up. Where is screen right? Right? So my current is going up, and of course by current, I've defined it from there's my current going up, current, and of course current is defined from a positive perspective, right? So that's my current. I'm referring to the movement of positive charge going up. which of course would then imply that the negative charge, like the electrons, are actually going down. All right. So my thumb is my current. My thumb is the current, and my fingers, the fingers here are actually the direction of the magnetic field. So the magnet, as you can see, the fingers are sort of going anti-clockwise, as is likewise the magnetic field drawn anti-clockwise. All right. Some other pictures of that are here. As soon as it opens, oh, that's not going to work, is it? Like that. Here's another picture for us to see. So thumb, current, direction of fingers is the direction of the magnetic field, anti-clockwise in this case. All right, that's case number one. Case number two has to do with a single flat circular coil. Right, let's look at that. Right, in this case, what do we have? Imagine you have on this end positive and that end negative, which means your current again is flowing that way, right? Flowing this way and going up. So on the side, let's call this side A. This is side A, this is side B. On side A, your current is flowing upwards, isn't it? Which also means, therefore, your thumb is pointing upwards. Your thumb is pointing upwards, which means if my thumb is pointing upwards, my fingers are going to align themselves, according to the right-handed grip rule, are going to align themselves anti-clockwise, right? So your fingers are sort of going anti-clockwise, aren't they? Your fingers are like that. Your fingers are like that. That's how it works. Anti-clockwise. Your fingers on this side, right? Going anti-clockwise. And of course your field lines is also adjusted anti-clockwise. But now, let's look at side B. Now your current has gone up and then comes down. Your current has come down. So again, your thumb, which is your current, is pointing downwards. Your thumb, which is your current, is also pointing downwards. This time, if your thumb is pointing downwards, your fingers are going clockwise, right? So your fingers are sort of pointing, wrapping themselves around here in that sort of general direction, right? Terrible at drawing. So your thumb is here. This is your thumb with the fingers sort of like that on this side of it, and of course pointing in the anti-clockwise direction. Interesting, right? But of course you'd have also noticed that the field is generally stronger here when the coils are closer together, when the coil flowing in the current is closer together, but then gets weaker as you get away from the current carrying coil. All right. I hope that makes perfect sense to you as it does to me. And then the next thing was our solenoid. Solenoids are really important. So important. What makes solenoids so important? You'll see. Just give it a few seconds. Right, here's a solenoid. Well, this time in our solenoid, we have many wires, perhaps wrapped around, the core of a tissue roll, right? That's what we have here. Wires wrapped around the core of a tissue roll, right? And of course, you can see that the wire, the current, this is definitely the positive side here. The current goes over and under, right? So as the current is flowing under, this is how we align our fingers this time. We're aligning the what? The fingers in that sort of direction. Now your fingers are the current and your thumb is the magnetic field. Before, our thumb was the current. This time on a solenoid, your fingers are your current. Of course, it doesn't really matter how you do it, strictly speaking, but for the solenoid, it's just easier to make your current the fingers, right? Which then means that the thumb is pointing towards the North Pole. I hope that makes sense. But of course, I was saying to you, what makes a solenoid special? Well, the solenoid is special because inside the solenoid, you have a uniform magnetic field inside, right? Inside the solenoid, you have a uniform magnetic field, as illustrated by my lovely parallel lines, right? So you have a uniform field in there, perfectly straight, parallel, in the solenoid. And as soon as they come out, of course, the field becomes weaker and they're not parallel anymore. But during the length L, you have a uniform field with perfectly parallel lines. That means if you were to draw a graph, maybe of magnetic field density against length, in the field you'll have a straight line. And then, of course, it starts to dip on those ends, doesn't it? It dips after where this is maybe L, I think. That's L from there to there. And then after L, length L of the solenoid, you have a decrease until 0 of the field. Special, yeah? Super exciting. All right, and then the Helmholtz coils, Holtz, I'm not Holzhausen, but Helmholtz coils. What does that look like? Here we go. Right. And they look something like, let me get a picture of them. Can I find a picture where you want it? All right, not quite what I had in mind. Where is it? Okay. So in terms of apparatus, it will look something like that, right? Something like that. Two parallel coils connected to a battery of some sort, right? Or a power source of some sort. But then in terms of the magnetic field, so you see, like this, or like that, right? You can see that. But in terms of the magnetic field, it will also look something like that, where you kind of have a parallel field in the middle and it starts to, lose strength in a sense after you leave the vicinity of the coils. Right. Well, that's those classical cases. But now let's discuss the important stuff, right? What is, for example, what are we talking about here? We have, for example, as you can see here in blue, a wire that's carrying current. What do we have there? A wire carrying current. And that wire, that, as you can see, it's connected to a cell or a battery there. And so my wire carrying current is then put in a magnetic field. Interesting, hey? It's put in a what? In a magnetic field. And because it's in a magnetic field, it begins to experience a force. Because you see, my wire that is carrying the current, because it has moving charged particles, it has a current. All currents have their own magnetic fields. So his magnetic field interacting with the existing magnetic field B creates a force, which we call the Hall effect, right? So basically you have two magnetic fields interacting with each other to create a force, right? And of course, to work this out, we use Fleming's left-hand rule. Fleming's left-hand rule, as you can see from my drawing there. I'm going to create another quick video just to show you what Fleming's left-hand rule works, but I've tried to do it and attach it to this video, and it's just not working well. And if I have to say all of this again for the 5th time, I'll probably go mad. All right, so Fleming's left-hand rule, you already have a pre-existing current. You're not making the current, because we use the right-hand rule when we have to make current by cutting magnetic field lines. So I'll ask you, if I say to you, make bread, make a painting, or make an image, which hand do you use to make things? You use your right hand. So right hand, when we are making the current by cutting the field lines. Left hand, there's already a pre-existing current. That's what we're talking about, Fleming's left-hand rule. And the formula, of course, then becomes F is equal to Bill sine theta. The force that's on the wire in the magnetic field is F is equal to Bill sine theta. B being magnetic flux density, current, I length of the wire in the field, L sine theta is the angle. Where's sine theta? Sine theta is here between the wire and the magnetic field. The angle is theta. Right? When do I get maximum force? Well, I get maximum force when my conductor is 90 degrees. My wire carrying conductor is 90 degrees to the magnetic field, maximum force. When do I get no force at all? When my conductor is parallel, because is placed parallel to the magnetic field. Then maximum force 90, minimum when it is 0. F equals Bill sine theta. Now we use F is equal to Bill sine theta to be able to do two things. One, to be able to define B, the magnetic flux density. But important for you to be aware when you have to go into the definition is theta 90 for the definition, current I 1 amp for the definition, length 1 meter for the definition. Let's try and define it now. Have you got that? It's a lot of process, isn't it? And I'm talking really, really fast, and I should really talk really, really slowly so that you understand what I'm trying to say. So I'm going to slow it down again. All right. F equals Bill sine theta, really important for the definition. And what is theta? 90 degrees. I should be 1 amp. L should be 1 meter. I hope that makes sense to you. Right, so let's make B the subject. If I make B the subject of F is equal to Bill sine theta, I get F over IL sine theta. But of course, sine theta is 1 because it's at 90 degrees. L, 1 meter, 1 meter, and I, 1 amp. Right, cool with that? So what is magnetic flux density? It is the force per unit length of a long straight conductor, force per unit length. Per unit length means 1 meter of a long straight conductor carrying 1 amp of current at right angles to the uniform magnetic field. At right angles to the uniform magnetic field. All right. Let's define the Tesla. Let's define the Tesla. Now the Tesla is the unit for B. The Tesla is the unit for magnetic flux density. Not an easy one to define, but let's have a stab. It is the uniform magnetic flux density when acting normally or at 90 degrees on a long straight wire carrying 1 amp of current causes a force per unit length on the conductor. All right, please spend a few minutes trying to work out the definition of B and the definition of the Tesla. It is certainly worth your time. So when does this work? What are the conditions? It works when 1, the conductor is not parallel to the magnetic field. Like we discussed, if it is parallel to the magnetic field, that doesn't work. If you put this wire here parallel to the magnetic field, not going to work. Terrible thing. And of course, it really works, or the conditions are that the force, your thumb, should be at 90 degrees to the plane containing B, your field. So your force, your magnetic flux density, and your current are all at 90 degrees to each other, as you can see in that illustration there. All right, I've tried to make this as short as possible. I hope that works. All right, otherwise, take care and best wishes for now.